Hey everyone, so this is lesson number 7 in the Trigonometric Identities and Functions unit, and so we're going to keep looking at some trigonometric identities and some more complicated proofs. In this blank lesson, it'll go over what parts of the trigonometric toolbox we have learned so far. So we've talked about the parity in trig functions, so looking at negative angles and what that bottom right quadrant tells us about them, cofunction identities, the quotient identities, and reciprocal identities, more related angles with cast rules, so that basically is a continuation of the parity. And then what we've talked about that's a little more new this year, compound angle formulas, double angle formulas, and the one Pythagorean identity that you've learned so far, and its rearrangements, the sine squared x plus cos squared x. We're going to talk a little bit more about those. I just wanted to go over the compound angle formula and how it's written, and just make sure you're comfortable with that. So sine of x plus y, that positive sign here matched up with the positive sign here. Sine of x minus y was sine of x cos y minus cos x sine y. So we're used to plus or minus being written like that. What I don't know if you've seen before is the minus plus, and that's just telling us that when cos of x plus y is what we're looking for, it equals cos x cos y minus sine x sine y, so the plus and the minus go together. And then this minus and plus go together. So cos of x minus y, we have a plus in the middle of these two terms here. So it's just a little bit more condensed version than having to write out both the sum and difference compound angle formulas each time. So that's all I have to say about that. We're going to use our Pythagorean theorem identity and see what we can do with it in creating a couple more identities that will be useful going forwards. So we'll start off with our Pythagorean identity, and we're going to divide both sides by sine squared theta. So if we divide both sides by sine squared theta, that's like dividing both these terms on the left by sine squared theta separately. And if we do that, sine squared theta divided by sine squared theta is 1. Cos squared theta divided by sine squared theta, that's cotangent squared theta. And we know the inverse of sine squared theta is cosecant squared theta. So that gives us another Pythagorean identity that we can use going forward. 1 plus cotangent squared theta equals cosecant squared theta. And of course we can rearrange that, and that'll give us some more identities, but that base identity is how we will remember it. We also get an identity if we do the same thing but divide by cos squared theta. So if I divide every term by cos squared theta, sine divided by cos gives us tan, so that's going to be tan squared theta. Cos squared theta divided by cos squared theta is 1, and the inverse of cos squared theta is secant squared theta. So our third Pythagorean identity is tan squared theta plus 1 equals secant squared theta. So that's just the last addition to our trig toolbox for now. And we're going to look at some examples of actually proving some of these trig identities. But just to wrap up that bottom of that first page, so when we're solving identities, we want to work with one side generally. As I said, you can play around a bit with both sides if you're finding it useful. And the trick to that in the future, if you have teachers or professors who ask you only to work with one side, is you can play with both sides and see kind of how you can get them to equal each other, and then work backwards from that and just show it all on one side. If you do have a teacher or professor who insists on only working on one side, again, I said that's okay because sometimes it can be useful. And so we're using our algebraic skills like substitution. We're going to have lots of fractions in these identities, some common factoring, even trinomial factoring. Those are all going to be useful tools to us, knowing how to manipulate our expressions and try to get them to look like what we want them to look like on the other side of the equal sign. Like I said, it's kind of like a puzzle, and the more practice you get on this stuff, the better. The more it's going to come second nature. You are relatively lucky where we're not going to have necessarily a test on this. You're not going to have to do it on the spot. You have some time to think things over and look at your notes and stuff when it comes time to an assignment. But it's still good practice to practice some of these problems over and over, and not necessarily the same ones, but the more you're exposed to it, the more comfortable you will be and the more second nature it'll be. Because I know this is quite a bit different than a lot of the math you're used to so far. So we'll look at a couple examples here. So we have sine 2x over 1 plus cosine 2x equals tan of 2x. So as I mentioned in previous videos, we want to start off with the more complicated side. Oh, this is not tan 2x, this is tan of x. It is important to note, though, that tan that's just sine over cos. So that's kind of a hint of we want to get to the point where we have a sine over cos happening here. But we are going to start off with the left side because that is clearly the more complicated side. So our left side is sine of 2x over 1 plus cos of 2x. We can use those double angle formulas. So sine of 2x, we have only one choice. Sine of 2x is equal to 2 sine x cos x. That's really our only choice there. We know we don't want a double angle because our answer only deals with single angles. So even if we get to the point where we get a sine x over cos x, we only have single angles. Again, we're always kind of comparing and seeing what hints we can get from our equation. We're going to need to get rid of this cos x in the top at some point. So that is our hint of which 1 plus cos 2x, which double angle formula for cos we want to use. It'll save us a little bit of time. So cos 2x, that was 2 cos squared x minus 1. Yes, there were two other versions of this double angle formula, but the fact that we need a minus 1 to get rid of this one, and we're going to want to get rid of that cos x, is our hint that maybe we want to use this one here. Again, a lot of that comes from practice. So we can simplify this denominator. The 1 minus 1 cancels out, and we just get 2 cos squared x. Our 2's are going to cancel out, and we have a cos x and a cos squared x, so we can cancel out a cos x from both, and that will leave us with sine x on the top and just a single cos x on the bottom. And as we previously mentioned, that sine over cos x, that is tan of x, and that is our right side. So therefore we solved we proved what we were setting out to prove. we got it to tan x. And that's all identities really are, is we need to get one side to look like the other. We need to prove that they are equal to each other. Look at number 2, which is tan of 2x minus 2 tan 2x sine squared x equals sine of 2x. So we have two different terms on this side. That is a pretty good hint that we want to start off with that left side. The left side is a lot more complicated. So we're going to start there. Left side, which is tan of 2x minus 2 tan of 2x sine squared x. It's not really immediately clear where we go from here. So we basically just want to start manipulating things any way that we can until things might become a little more clear. What we do know is here we have two terms, here we have only one. So one way that we can kind of combine things, so we can look for a common factor. We have a tan of 2x in both terms. Let's factor out tan of 2x, and we'll get left with just a 1 in our first term, and 2 sine squared x in our second term. That 1 minus 2 sine squared x, that is one of the cosine double angle formulas. So that allows us to get just one single term here. Tan of 2x times cos of 2x. Again, as I mentioned in a previous video, it's generally easier to get things eventually down to just sines and cosines. So the tan of 2x, we can turn into sine of 2x over cos of 2x. And that's multiplied by cos of 2x. And so because it's multiplied, those are going to cancel out. And we just get left with sine of 2x, which is our right side. So we've proved what we set out to prove. QED, that Latin phrase, that basically means that we've proved what we set out to prove. And we can move on to number 3. Secant to the power of 4b minus 1 equals 2 tan squared b plus tan to the 4th b. The completed example starts with the left side. I'm going to start with the right side just to show you something a little bit different. We have a tan squared and we have a tan to the power of 4. So we can factor out a tan squared from both sides. And we're going to get left with 2 plus tan squared b. And so from here, it's not immediately clear where to go, but we know we need to deal with secants instead of tans. We have two different tan squared b's. We can use the Pythagorean identity and rearrange it, which tells us that tan squared theta should be secant squared theta minus 1. So we're rearranging this identity here. And we're going to plug this in for tan and see what happens. So we get secant squared b minus 1 and 2 plus secant squared b minus 1. And we can simplify that second bracket. And we get secant squared b, 2 minus 1 is plus 1. And this, we get a difference of squares. We have one term minus another, and then the same two terms, but we have the first term plus another. So this is going to be secant squared b squared minus 1 squared. And if we simplify that, secant squared squared, secant to the power 4b minus 1 squared is 1, and that is our left side. So therefore, we proven that one as well. I see actually there was two examples for that one. There was one starting with the right side, so I thought I was doing something a little bit different, but that one is there as well. Number 4, sine of x plus sine of 2x all over 1 plus cos x plus cos of 2x. And all of that equals tan x. So we're going to start off with our left side. That is the much more complicated side. We want to get that to equal tan of x. So we want to get that to be, we know tan of x, again, is just sine x over cos x. So we need to eventually get just a single sine x in the numerator and just a single cos x in the denominator. We have double angles here. No double angles in our answer. So we're going to expand those double angles. So sine of 2x was 2 sine x cos x. And in the denominator, again, we have to make a choice with our cos x, or cos 2x. We have those 3 different double angle formulas. We only need to deal with cos x. We only need to have a cos x in the bottom. So we'll choose the one that only has a cos x in it and see if that works out. And right away, that minus 1 and that positive 1 are going to cancel out. So we have sine x plus 2 sine x cos x all over cos x plus 2 cos squared x. In the top, we can factor out a sine x, and we get left with 1 plus 2 cos x. And in the denominator, we can factor out a cos x, and we get left with 1 plus 2 cos x as well. So we have that exact same term being multiplied, so we can cancel those out, and we get left with sine x over cos x, which again, we mentioned that's just tan x. So that is our right side. So that means that we're okay. We've proven that identity. We got one more example here. Number 5, cos cubed x plus sine cubed x equals cos x plus sine x times 1 minus sine x cos x. So we'll start off. Our slightly more complicated side is our right side. We have a little more going on there. And we have two things being multiplied together in our left side that we're trying to get this to match. There's nothing multiplied. We just have two different terms. So that is our clue that we should multiply this out. We should use FOIL. So cos x times 1 is cos x. Cos x times negative sine x cos x is going to be negative sine x cos squared x. Because we have a cos x times a cos x. Sine x times 1 is sine x. And then sine x times negative sine x cos x is going to be negative sine squared x cos x. There's a couple different ways that we can go about this. Just trying to see if there's any that jump out at me that aren't the way they did it in the completed lesson. That's probably the easiest. So, Pythagorean theorem, identity, we can turn this cos squared x, into a 1 minus sine squared x. We're getting rid of the fact that we have both sine and cosine happening in the same term. And similarly, in our last term, we can turn our sine squared x into a 1 minus cos squared x. And that way we only are dealing with coses in that term. And we can multiply out, use distributive property and get rid of our brackets. And we get negative sine x times 1 is just negative sine x. Negative and negative gives us a positive sine cubed x plus sine x minus a cos x, then minus negative gives us a positive cos cubed x. So we have a cos x minus a cos x, sine x, and then negative sine x, and we just get left with a cos cubed x and a sine cubed x, which was our left side. So that is what we're looking for. So therefore, these are always going to be equal for any single angle x. So that's what makes it an identity. So that's the end of this lesson. You'll hear from me again soon in the next lesson. Have a good day and goodbye.